So this is section 2.7, rates of change in the natural and social sciences. So this is a section on where you might see the idea essentially of the derivative, the rates of change, kind of in the real world. Not kind of in the real world, in the real world. Well, kind of in the real world for the first question, because it does, talk about a particle, which could be anything, and gives you a function. So the first example is the idea of motion. So motion can often be written, modeled by a function. So that's what you're seeing here. So notice it says a particle moves along the x-axis. Its position in meters at time t seconds is given by this function, x of t, and then we have this rational function. So what you want to understand is the idea is if it's a particle, it could move along the x-axis, it could go here, it could go back, it could do a couple different things. It's not like it's just going to move along the x-axis like this. In this real world capacity, the particle could go back and forth. And it could go at different speeds, things like that. So first, we want to note that t is greater than or equal to 0 because it is time, and we cannot turn back time. And then for A, it asks us to find the velocity at time t. So this, of course, just means find the derivative. And because the function is a function of time, that just means find the derivative. So you need to find x prime of t. And if you want, you can go ahead and pause. And of course, you need the quotient rule in order to get the answer here. So go ahead and see if you can find the derivative and then come back and see what happens. So I'm going to take the derivative of the top and I get 1. And then I'm going to leave the bottom, 1 plus t squared. In the quotient rule between the two terms, we have a subtraction sign. And then I'm going to have the top, and I'm going to take the derivative of the denominator. And then it's going to be all over, we don't want to forget that, our denominator squared. So now I'm going to have my numerator, 1 plus t squared minus 2t squared. That's all over 1 plus t squared squared. I'm not going to multiply that out. There's no reason to do that right now. So it looks like I will have 1 minus t squared over 1 plus t squared squared. And that is our velocity at any time, okay, at time t. Then we get the question, when is the particle moving to the right? And so, like I said, if it's going along the x-axis, it could be going this way, it could be going this way. So we want to know, when is the particle moving to the right? And what you should understand is that that is in the positive direction. This way is the positive direction along the x-axis. So really, another way to think about what this question is saying is that the particle is moving to the right when x prime of t, which understand again, that's the velocity, v of t, is greater than 0. So that's really all we want to find. All we want to do is find out when is that derivative that we found greater than 0. That's when the particle will be moving to the right. So if I set 1 minus t squared all over 1 plus t squared squared, and I do an inequality, we want to know when it's greater than 0. That's what we're trying to find here. A couple things to think about, stuff that we already know. Looking at the denominator, we have this 1 plus t squared squared, and that's always going to be positive. 1 plus t squared is always positive because t squared is always positive, and then if you take a positive and you square it, it's always positive. So the only thing that could make a difference here to us would be the 1 minus t squared. We want to know when is that greater than 0. It's the only thing that matters. And, you could look at some values and think about, okay, well, what values of t could I put in? And they will give me something that's greater than 0. The more formal way to do that, of course, is to notice that this is a quadratic. It is a difference of squares. So it is going to factor like this. And then this is a quadratic inequality. So the best idea to do is to draw yourself a little number line where t is time. So notice that the two values that make this 0, because that's where it would change, It would change on either side of those values. We know that the values that would make this 0 would be 1 and -1. So if I put those values here, -1 and 1, and then I just look at what happens on each of those intervals, what happens between -1 and 1, what happens on to the left and to the right, then that's going to tell me when this derivative is positive and when it is not, which means the velocity. So I can pick something that's less than -1. So let's say we put in t equals -3. So the idea is just we're putting these values back into here and we're seeing what we get. So if we put in -3, you can see that we get 1 minus -3 squared. No matter what you put in, that's going to be positive. So -3 squared is 9, and 1 minus 9 is a -8. So that numerator is going to be -8, which is not positive. So we have a negative here. So I'm doing this just again to determine for what values of t do I have a positive value. Now if I put in t equals 0, you can see, because that's between -1 and 1. If I put in t being 0, I get 1 minus 0. And 1 minus, so again, I'm putting that in right here. 1 minus 0 squared is still just 1. That's a positive number. So I have a positive, meaning that the derivative is positive between -1 and 1. And then after 1, let's say we put in something like t equals 3. Again, it's going to be the same as the other side. So we would get 1 minus 9, which is a negative value. So we have a negative. So the thing also to think about, however, is that the fact that t has to be greater than or equal to 0 matters because it's time. So another option that you have is essentially to think about this kind of cutoff right here, and that we really only care about what happens between 0 and 1 and what happens after 1. Because it doesn't really matter that, because when we see that derivative, it's just a function of t. It doesn't care about the real world aspect of this. We have to care about that. So once we kind of realize, okay, t has to be greater than 0, now that just reduces the space where we could have the positive or the negative. So as we can see, once we go at 0 and then to 1, we have a situation where our derivative is positive. And because it's from anywhere from -1 to 1. So now we can just say from 0 to 1, we have a derivative that's positive, therefore the velocity is greater than 0, and the particle would be moving to the right. So we just have to write our answer down. That's what we have to do now. So I can say the particle is moving to the right, since that is the question. Moving to the right when t is greater than or equal to 0, less than or equal to 1. And then realize that what this is telling us is that after t being 1, you have that negative. And when you have that negative, that means that the derivative is negative, the velocity is negative, and in that case, the function would be moving to the left. So we don't want to think about that. But in no point in time should our t be negative. So there we go. That's it. Okay, more to do with this question. All right, find the total distance traveled in the first 4 seconds. So the thing to understand that's important about this is when we talk about total distance, that means that if the particle goes like this, blah, 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 but then goes blah, 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 we need to add this distance and this distance to get the total distance. So it matters if the particle is moving forward or backward because that's gaining some distance during the time that it's doing that. So what we care about, and this is from the last thing, is we care about when the function is moving forward and when it's moving backwards over the first 4 seconds. So for our purposes, what matters is when t equals 0, when t equals 1, this is all from the last piece, and then because it's the first 4 seconds, we care about t equaling 4. So what we know, of course, is that we had the function moving forward from 0 to 1. And then after 1, it was moving in the opposite direction. It was moving to the left. And so I'm going to put a minus there. And then it just matters that we finish at 4. So in order to find the total distance, we want to find basically where is the function at these different t values. So we're going to go back to our original function and find x of 0, x of 1, and x of 4, because it's all, remember the function is x of t. So if you want, you can pause, take a minute, see if you can come up with the position values, these are position values, for the function at those 3 points, and then see if you're right. Okay, so the first thing I'll do, I'm going to have 0 over 1 plus 0 squared. Oh, that gives me 0. So the function is at t being 0 and x of t being 0 at 0. I have 1 over 1 plus t squared. So I have this, whoop, whoop, and that's 1/2. And then at 4, I have 1 over 1 plus 4 squared, like that. So 1 over 17. 4, because we have a t at the top. Excuse me. 4 over 17. Okay, I was just getting crazy with my ones. So now that we know where the function is on that line, on that x-axis, so it's like it starts at 0, and then at 1, it's at 1/2. But then notice that at 4, it's at 4/17, which is less than half, so it's gone back. So what we want to do is we want to add this distance plus that distance, and that'll be the total distance that it went. So the way to think about that is really just that the total distance is essentially, 0. It's not anywhere, it's just at 0. So it goes from here to here, and so we have 1/2 plus, and then what it does is it goes from here back to 4 over 17. So we need to take 1/2, subtract 4 over 17 to see how far it went to get to that 4 over 17. So that's going to give us 1/2 plus, and then we just need to do this, subtraction. So this is 17 over 34, and this is 8 over 34. So I'm just making a common denominator there. So then I have 1/2 plus, and then that's 9 over 34. Woo! I'm doing a lot of weird denominators there. So we've already decided that that's 17 over 34 plus 9 over 34. And that's going to give me, let's put it right here. That's going to give me, it looks like a 26 over 34. So just simplifying that fraction gets us 13 over 17. And it looks like our units are meters. So the total distance is 13 over 17 meters in the first 4 seconds. And that's it. So again, you're moving along the x-axis here, and you have 0, and for example, you have 1. And what it does is, this is the x-axis, so understand that. So over time, what you've done is you've gone to here, and then you turn around and you go back. And so we just want to make sure we're adding up all of those intervals. And that's how we get 13 over 17. Okay, now when is the particle speeding up? So this is the last bit of this question. When is the particle speeding up? Okay, so this is a key thing to understand. The particle is speeding up when, let's see, I'll put something around this. When the velocity and acceleration are the same sign. Okay, speeding up. So the idea here is, if you're moving in the positive direction and then you put your foot on the gas, then you're going like this, your velocity is positive and your acceleration is positive and you're speeding up. But because we have the idea of direction here, you could also be going this direction. Your velocity is negative. If your acceleration is also negative, then you're speeding up, but in this direction. So we care about two different things. We could be in this direction or we could be in this direction. But the idea is your they should have the same sign. So either both positive or both negative. That's what I mean by that. So what we would need is to find the second derivative. So we need to find acceleration at time t. That's the same as the second derivative of the original function. So that would be the first thing that we need. So I will, if you want, go ahead and do this. I'm gonna need this space here, unfortunately, but it is the quotient rule on the first derivative to the second derivative. It's using the quotient rule again and then simplifying. If you do that correctly, I'm just gonna tell you what it is. If you want, you can pause, try it, and see if you're right, if you want more practice with the quotient rule. But the answer that does come out is 2t, t squared minus 3 over 1 plus t squared cubed. Okay, so what we want to think about here is, this is our acceleration. We want when velocity and acceleration are the same sign, so both positive, both negative. We already know things about the velocity, so we're going to be able to use that. So I'm going to come maybe over here. Let's see how I want to do this. Let me come back over here. Okay. Here's what we care about. Denominator, still always positive for acceleration. But now we have 2t times t squared minus 3, and we want that to be greater than 0. And I mean, basically what we want to look at is, when is it greater than 0? When is it less than 0? These are already things we know about the velocity. So really we just want to check on this. So a good thing to think about here is that this numerator could be equal to 0 when t equals 0, or t equals plus or minus the square root of 3. So if you take t squared minus 3 and you set it equal to 0, you're going to get t is plus or minus root 3. Now, of course, we still have the idea, let's make sure I have the space here. So let's say what we care about really is when that after t equals 0. That's important to us. So we can think about kind of two lines here. Here's acceleration at time t. Here's velocity at time t. We already know velocity at time t. We already know that at t equals 1, the velocity changes. So what we know is that the velocity is positive until 1, and then it becomes negative. What we know, so it's going in the positive direction than the negative direction. But now we also have to consider, we have time equals 0, that's already on here, plus or minus root 3. So we don't have to care about negative root 3 because it doesn't matter, but we have to care about the positive root 3. And that's going to be somewhere over here. So t equals the square root of 3 is going to be somewhere out here. It's just bigger than 1, so it's going to be somewhere out here. What we know about velocity is that we have positive, and then we have negative, and then that stays negative. We know that after t equals 1, the velocity is negative, so I can do that. So now really all I care about is what's happening with the acceleration, and then I just have to look and see where they match, so where they have the same sign. So we need to pick a value between 0 and 1 for our acceleration. And if we pick, say, a half, you should notice that if I were to pick a half, the first part of my acceleration numerator here is going to be positive. The second part, if I take a half and I square it and I subtract 3, that's going to be negative. So a positive times a negative is a negative. So those signs are not the same. So it would not be speeding up from 0 to 1. And then I want to pick something from 1 to root 3. So I could pick something like 1.5 would work. So 1.5, if I put in 1.5, again, this first part's just going to be positive. If I put 1.5 into here, so I mean, it's pretty straightforward. I just need a basic calculator, which is downstairs, so I'll have to use my phone. But if I put in, I never use the calculator on the phone because I have 800 calculators. Okay, if I take 1.5 and I square it, I'm going to get 2.25. And if I take 2.25 and I minus 3, that's still going to be negative. So again, I have a positive times a negative. I'm going to have a negative here. But I have the same signs, so that matters. That's telling me that it's speeding up, but in the negative direction. moving to the left. If I pick something greater than 3, or root 3, so say I pick something just like 5. Again, this piece always positive, but now this piece, I mean, I take 5 and I square it, I get 25 minus 3, that's a positive number. So I get a positive times a positive, that's a positive, but it does mean that I have a difference in the signs after the square root of 3. So what it does tell us for our purposes is that the particle is going to be speeding up between 1 and root 3 seconds. Okay, so the particle is speeding up, but in the negative direction, speeding up from 1 to the square root of 3. And what it does mean is that if it's not speeding up, then when the signs are different, then it's slowing down. So your velocity might be positive, and so you're going like this, but if your acceleration is negative, then that means that you're actually slowing down. And, so imagine putting on the brakes. You're going forward, but you're putting on the brakes. And so that's what's happening there. And that's happening as well after the square root of 3. So after the square root of 3, your velocity is actually negative, but your acceleration is positive. So that's also going to be a situation where you're slowing down. Okay, and that is our first example for rates of change in the natural and social sciences.